Over the next several videos, we're going to be talking about electric potential and relating it to our various quantities that we've already discussed, such as force, electric field. We're going to come up with several different equations, and which one you use is going to depend on what information is available and the particular problem. So definitely pay close attention as we're looking at all of these different forms. So to start and introduce our electric potential, let's consider moving a point charge from point A to point B in an electric field. So let's start with our basic Coulomb's law definition. So as we've seen previously from Coulomb's law, we know that the force is equal to Q times the electric field. And so throughout our explanations, unless we say otherwise, we're going to assume that this Q just represents some positive charge. So if we go back to sort of our basics physics definition, we know that our work is equal to force times the distance. So let's just say in general, work equals force times distance. So let's consider a differential length to move this point charge along. So consider a differential length, and let's just call it dl. Okay, so if we have some differential length vector, we want to find the work done by moving that along some differential length. We could just say it's dw is equal to the force dot dl. So if you recall from physics, we also had some cosine term in here, so that's where why we're going to use our dot product here. So we can then say that as we have written above, and so sorry I've left out a negative sign here, so this is negative just because we're going to come back and talk about later as far as when is the work being put into the system and when is the system sort of producing work. So we can use our Coulomb's law equation of F equals Q times E and rewrite this as negative Q times E dot dl. So if we want the total work done in moving between 2 points, all we have to do is integrate that differential work. So total work moving from our point A to our point B is given by W is equal to negative Q, so I can go ahead and pull that Q out because that's just going to be a constant, integral from A to B of our E dot dl. Okay, so that's sort of a basic definition that we're going to use for the work done by an electric field on a charged particle moving in it. So what we can do then is we can normalize the energy to the charge. And if we do that, that's when we get our potential difference. So let's normalize that energy W to our charge. And so that's going to give us our potential difference between those 2 points A and B. And so of course potential difference is just another way to say voltage. So potential difference between, let's clean that up a little bit. All right, between A and B. And so by normalizing that, all we do is we divide our omega by Q. So we would have then VAB is equal to W, sorry, not omega, W, divided by Q, which is just going to be equal to negative the integral of A from A to B of E dot dl. And so this is one relationship for our electric potential or voltage that we're going to use in certain cases. So we're relating the voltage to the line integral of the electric field. So let's make a couple notes about this voltage equation and this voltage in general. So the notation is actually backwards from what we use in most of our other classes. I'm going to keep it this way just to be consistent with the text so it's not too confusing. But our VAB is actually the potential at B referenced to A. Sorry, this is acting up a lot lately, so the potential at B reference to our point A And so we can keep in mind that VB and VA are absolute potentials. And we'll talk about where those are sort of implicitly referenced to here in a later video. So these are absolute potentials. And we could say that our VAB, based on the definition above, is equal to VB minus VA. So it's our absolute potential at B referenced to our absolute potential at A. So for instance, we could come down here and we could say, well, if we have point B over here on the right and point A over here on the left, well, at the left we have potential VA, at the right we have potential VB. So we're saying this voltage positive at B, negative at A would be VAB. And so again, this is different notation than what we use in other classes, but I'm going to keep the notation in this class similar to what we have in the textbook. So again, just be very aware of that. So we can talk about sort of two general situations with our potential difference then. So if that voltage is less than 0, so if VAB is less than 0, then this is going to be a loss in potential energy. And so in potential energy as we're moving that charge from point A to point B. So loss in potential energy in moving our Q, which again, remember, we're assuming that that's a positive valued Q from A to B. And ultimately what that means is that work is being done by the field. So our field is moving that charge from A to B. And so let me just sort of draw schematically here. So if we have some charge here, Q, which is going from A to B in that direction there. Okay, so the other case, of course, is if we have a positive electric potential. So if our VAB is greater than 0, what that is a gain in potential energy. And so a gain in potential energy as, again, we're moving Q from A to B. So as our Q goes from A to B. And ultimately what that means then is that some external agent is performing work to move that charge. And so if we think that this, so if we consider that this VAB as shown here above is positive valued, then what we're saying is that we have some external agent which is causing this positive Q to be moving sort of in the opposite direction that it would normally want to be moving. So a positive charge moving towards the other positive charge at point B. And in doing so, it's gaining potential energy. So a couple other notes about just our VAB in general is we're going to come back and talk about this a little bit later on in more detail, but it turns out that our VAB is independent of the path we take. So independent of the path taken. And then, of course, as you're well aware, hopefully by now, the units for our VAB is dimensionally volts, but something that can oftentimes be useful is to remember that volts is joules per Coulomb. And so if you forget, we can easily remember that from our energy equation, or rather from this equation here, where we have related our potential difference as the normalized energy to the charge, so W over Q. So in the following videos, we're going to take a closer look at this potential equation. We're going to sort of put it in some different forms. And again, which form we use is going to depend on what information we have available and what we're trying to find.